Hi everyone. So we'll start the session around I guess 7 past 5. So 7:05. So I guess we can start now. Just a second. Get up here. Welcome to this lecture. This is the problem solving session, week 2 of the course titled as Semiconductor Devices and Circuits. And my name is Shomnath Bhattacharjee. So I'll briefly describe about myself and then we'll start the session. So as previously already I have told this. So my name is Shomnath Bhattacharjee. I am currently pursuing my PhD from IIT Jodhpur, and my research domains are related to flexible and organic transistors for neuromorphic computing. And I have previously done my BSc in physics and also MSc in electronics. So The scheduled time of my classes are every Sunday from 7 to 9, and we'll move on to the course layout. So this is a 12-week course, as we all know, and the first week was on excursion in quantum mechanics, and we have understand the like basic structure, like through the Schrodinger equation, how to solve everything and those things. So in this week, we'll learn about excursion in solid state physics, which is the second week of this course. So the like if we want to break the total course in three main or major parts, those were the chronic penny model, different types of solids like the semiconductors, metals, and those things. And finally, we have learned some basic information about the crystals. So we'll start with the basic recap of this week, and then afterwards we'll move towards some basic problem solving and those things. Yeah. So to start with this, like in the first week, in the second week, we have learned the, sorry, Pauli's principle. So what it states is that no two electron can possess same quantum numbers. So this was the basic starting point of this course, and afterwards we have learned the energy band splitting effect. Based on the distance between two adjacent atoms, we have known how the energy band splits, and so it is known as the energy band splitting effect. Then we have learned the chronic penny model. So I'll go through this a bit. In this chronic penny model, what was the main concept? It was like this. So I'm only drawing two of this, but there are multiples of these. And here is the Fermi level. So this energy band, the physical energy band, looks very similar to these kind of a band, where we can draw it like this. So main like reason to consider this band as a rectangular one, because we have already solved the Schrodinger equation in case of some rectangulars or square walls and the wells. So that's why we are considering it like this. So, so this well kind of a structure is very periodic in nature. This would look something like this. And afterwards, yeah. So afterwards, what we can consider is that so the wall is nothing but a structure like this. Okay, nothing but a structure like this. So like we tend to find a basic like periodicity between these two things. Sorry for my mistake. So this one will be much smaller, and this one would be much. So this should look like this. This looks like this, and we can term this well as A and this energy area as B. So from this, what we can consider is that the solution for this area is psi A and the solution for this area is psi B. And to consider the limits for this, the boundary condition to get the boundary conditions, we can divide it like this. So we can clearly see that this is the part or the unit where it repeats for multiple times. And let's say this is x equals to 0 and this one is x equals to a naught. So if this area is b naught, it should be x equals to minus b naught, and this point should be x equals to minus a naught minus b naught. So these are the terms we have already got, and from this what we can do is, just a second, yeah, from these, and we can get the lattice constant, which is lattice constant. We can consider a lattice constant, that is a. It will be nothing but a naught plus b naught, the sum of a naught and b naught, the sum of this well, this area and this area. Okay, so what we get as a solution is that psi a equals to a of a sine of alpha x plus p of a, I'm sorry, p of a cos of alpha x. And similarly we get psi b of a similar kind of a result, that is a of b of sine beta x and b of b as cos beta x. Now we have to find out what are the alpha and beta terms. So from this we can get that alpha equals to root over 2me by h cut, while from this we can get beta equals to root over 2me minus, if we consider this as, let's say, u equals to 0, so we can consider this point as u equals to u naught. So this will be E minus U naught, the energy of the well, divided by H cut. So in this case, we have to consider E is greater than U naught, that the energy, this energy level is much less than the E value. And then there will be another case, right? So the case 2 will be if E is less than U naught, that is if beta is complex, then what will happen? So the value of beta in that case will be I multiplied by this, as u is greater than e, this divided by h cut. So this will be the solution in case of if beta is a complex number. So what will happen, that, I'm sorry, just a second, yeah. So if this is the case, so there will be a real case and a complex case, yeah. So we have to find out the boundary conditions. So there would be the basic boundary conditions considered here. The first boundary condition is sorry, let's continuity condition, that states that psi A and psi B should be continuous. So if we consider this point, just a second, yeah. If we consider this point, at this point, what happens that at this point psi A should be x equals to 0 and it should be equals to psi B when x equals to 0, because at this point psi A and psi B both corresponds to this point, this line. Okay, So this should be a first boundary condition. Based on this, the second boundary based on this, our second boundary condition would be continuity of the derivatives, that is nothing but del psi a by del x when x equals to 0 should be equals to del psi b by psi del x when x equals to 0. Apart from that, we need some more boundary conditions. So here we have considered a special boundary condition known as the Bloch's condition or Bloch's theorem. So what we consider in this, that as this is a repetitive unit cell, so whenever there is a repetitive unit cell, let's draw this, I guess. So whenever there is a repetitive unit cell, the amplitude of this section, just a second. So as we have considered this, so this was 0 when x equals to 0. This one was a naught, this one was minus b naught, and this was this one was this. Okay. So in this case, what we have considered is that this at this point, sorry, just a second. Yeah, at this point, psi a at x equals to a naught. So I am talking about this line, right? I'm talking about this line. This should be equivalent to the amplitude of this line. So this one would be psi a, and for this case it should be psi a naught e to the power I k a. That is the lattice constant. So we can write it as psi a x equals to a naught e to the power of I k a, or we can write it as sorry, this one should be this psi b x equals to minus b naught. So we can write it as this minus b naught, and psi b when x equals to minus b naught e to the power of I of k of a naught plus b naught. So based on this, we can write these two would be same. Okay. So the condition would be psi of a when x equals to a naught should be equals to psi of b when x equals to minus b naught e to the power of I k a, that is a naught plus b naught. So this should be the Bloch's theorem, and the fourth one would be the derivative of the Bloch's theorem would be also continuous. So derivative of Bloch's theorem. So that is nothing but this thing del psi x when x equals to a naught equals to del of psi b psi x equals to minus b naught e to the power of I k of e naught plus b naught. So these are the four major boundary conditions, and based on these conditions, what we can get is that we get a function of energy that is, let's say, f of e, which is equivalent to cos of e into a multiplier that would be we can write it as k of lattice constant, that is a, or we can write it as k of a naught plus b naught. Okay, so now we know that a cos theta value lies between this from minus 1 to 1, And based on that, we can also say that the value of this function of energy also lies between this. So if we plot this in a function of energy, and this would be the energy. So if we plot this, it would look like something like this, where the values keeps on decreasing. Okay, so if this is the value, and let's say this is the value of 1, and this is the value of -1. So what will happen that whenever the data is in between this, so whenever the data is in between this, the value of energy is permitted, and this as well. There was something, just a second. Yeah, so these values are permitted, and this raised values, that is this value, is not permitted as it's going beyond the value limit, that is 1 from -1, this area, and also this area. There is an invalid state as well. So I guess I'll just change the color, otherwise there will be an issue. So this is an forbidden area, this is an forbidden area, while there are these discrete patterns of energy. So the energy band would look something like this. So these are the permitted energy bands, while going beyond the limit suggests that it is an forbidden energy gap. So this specifies the concept of energy band gap. The energy band gap concept comes from directly from this thing. And so this was the basics of the chronic penny model. Apart from that, we have learned the concept of metals, insulators, and semiconductors. So based on the structure of this, already form the concept of this band structure. So we can divide the solids into three major parts, that is the metals, the semiconductors, and the insulators. So so I'll briefly go through this because this is a basic concept. So at room temperature, a metal structure is something like this, where we have the conduction band and we have the valence band. So this one is the conduction band and this one is the valence band. So this is CB and this is VB. So the first thing is that overlapping band architecture is there. Second point is that the energy band gap is zero. Okay, so this is the structure of a metal, whereas at room temperature, if there is a very small gap between these two bands, and the gap may be between 0.5 electron volts to maximum of 2 electron volts. So this structure is called as a semiconductor, and like it has a very small energy gap, and whereas the last one is, if there is a very large gap between these two structures, this is called as an insulator. this gap is more than 2 electron volts. So this is called as an insulator. So although there are like few mobile electrons in the conduction band, still like it is very less because the total conductors divided by the total area is very less here. That is the density of charged carrier is very less in this case. So apart from this, there are few exceptions like let's say the wide band gap semiconductors and those things, which you guys can like learn directly from like sources. And then we have learned about the, let's go to the next page maybe. Yeah. So then we have learned about this concept called hole. So what is a hole? Hole is nothing but a vacancy left by a mobile electron. Okay. So if there are, let's say, two energy bands, so if this is called EC, EC is the lowest conduction band energy, and EV, that is the highest valence band energy. And there is a gap of EG, that is the energy band gap. So this gap is called the difference between this. So that is EC minus EV, that is the energy band gap between these two. So here there are electrons. Here are several electrons, whereas here there are no electrons in the this one. So if we give let's say a bit of temperature, or let's say a bit of voltage to this electrons, what will happen that these electrons will jump to the conduction band. This is the conduction band, this is the valence band. And when these electrons jump to that space, there will be a vacancy of the charge of this electron, which is called a hole, and the electron will be here. So these kind of electrons are called valence electrons or band electrons, and these kind of electrons are called free electrons. So this is the concept of hole, whereas we already know the concept of electron and also the protons. So based on this, and yes, from this one as well, so we have also learned about the condition of thermal equilibrium. So this condition is called a thermal equilibrium, where we are not giving any kind of a external temperature, no external light source or something, and no external voltage as well. So how the electron is getting like getting energy to cross this forbidden gap or the energy band gap? So it's gaining the energy directly from the environment. So as this is not at the temperature of 0 K, let's say it's at room temperature, that is nearly 300 K or something. So it's getting the energy directly from the environment itself. So apart from that, we have learned about different kind of a semiconductors, that is the intrinsic semiconductor, or let's say as pure semiconductor. So why it is called pure? There is no external impurity, or in this case we can say no doping. Okay. So another concept is that intrinsic carrier concentration. So what is called an intrinsic carrier concentration? Intrinsic carrier concentration is number of electrons per unit volume in the conduction band. We can term it as N, and similarly another point would be number of holes per unit volume in the valence band. We can term it as P, let's say. So as the number of electrons jump from the valence band to the conduction band is exactly same as the number of holes generated. So we can say that N equals to P. So we term it as Ni, that is the intrinsic carrier concentration. And for a crystalline silicon, the value of Ni is 10 to the power 10 per cc at 300 Kelvin. So the amount of Kelvin is very much necessary, that at how much Kelvin the value is what, because depending on this temperature, the value of this intrinsic carrier concentration changes. So another concept we have learned is the concept of electron drift. So what is electron drift? Basically, we can say that it is the movement of electron due to the applied electric field, or let's say voltage source at the terminals of the said solid. So how to explain this? So based on the voltage source we have based on the electric field we have given to the solid, there would be a migration of electrons towards the side, and there would be a migration of holes towards another side. So this is called the phenomena of electric drift, electron drift. So we term the electron drift as a basic phenomena, and based on this electron drift there is a velocity gain, so which is called the Vd, or that is the drift velocity, and this drift velocity is equivalent to the applied electric field. So this is the applied electric field, and we can write it as Vd equals to mu. So this mu thing is a very important parameter, as we all know, that is mobility. So from here the concept of mobility comes, where so this mobility can be written as mobility, or we can say effective mobility, or mu effective. So we can calculate this what do we say, like this factor from different phenomena. So based on that we can write it as mobility through the lattice structure, mobility through the defects and mobility from other parameters. So this equation is called the Mathiassen's equation or Mathiassen's rule, and we can like estimate the values of mu L. So mu L is nothing but from the lattice. So based on the scattering phenomena, and also through the concept of phonons, through the concept of phonons, we get to know that mu L is equivalent to T to the power minus 3 by 2. So let's talk about phonons. So phonons, if we can imagine, the atoms are connected through springs of this kind. So if there is this, so the architecture is like, so sorry. So this, due to the vibration, due to the, let's write it down, then I'll tell this. Due to the vibration in this kind of a springs, there is a generation of localized traveling wave. So these kind of a localized traveling wave is called phonon. So from this concept of phonons, we can understand that mu L should be equivalent to T to the power minus 3 by 2. Apart from that, we can also derive mu D, that is from the defects, which will be this, sorry, 3 by 2 and divided by n, and this is based on the charge defects, and based on the charge defects, so we get to know, oh sorry, I guess here I have written it wrong. This would be like this. So this is called the Mathiassen's rule, and after that we have learned the concept of effective mass. So there are two concepts. There are the concept of rest mass and the effective mass. So rest mass of an electron is the mass we consider, that is m, 9.1 into 10 to the minus, sorry, 1631 joule. Whereas, yeah, who was raising their hands? Yeah, go ahead. Okay, and there is the concept of m star, or that is the effective mass. So to calculate this effective mass is nothing but through this. Okay, that's fine. From this, so here t call is the mean collision time, vd is the drift velocity, mn star is the effective mass. So from this we can derive the value of mobility, that is q of t collision divided by mn star. So this is how we get the value of this effective mass. So apart from this, we have the last module was the concept of crystals. So there are different types of crystals. Those are the monocrystalline solids. So what are monocrystalline solids? This is long range ordered solids where there is a long range order like this, and this follows the pattern completely. So there are long range orders. Another one is the polycrystalline one, that is the polycrystalline solids. They like here are some like there may be some long range orders, but these are like limited like what do we say, like these are spaced in a very limited range, so we can say it as the intermediate range order. So these kind of structures are like this, let's say. So there may be a structure like this, while there may be a structure like this, and again there may be a structure like this. So we can basically create separate tile kind of a structure from this, where there are like ordered structures, still there are difference between these kind of a tiles. So tile like structure. And the last one is amorphous solids. So what is amorphous solid? There is a very short range order, and it is full of defects as well. Okay. From here comes the concept of Bragg's law as well. So what is Bragg's law? I'm not going into the like the basic derivation of the Bragg's law and those kind of a things, but the basic concept is that in a in a structured solid, crystalline solid, if there is a very high energy electron beam coming, and it's going from here, let's say, and, and this angle is, let's say, theta, and which is called the grazing angle, and this is the space between this, the lattice constant is d. So the Bragg's law states that for constructive interference, n lambda should be 2d sine theta, or we can say the value of d would be n lambda by 2 sine theta. So this is the Bragg's law, where you can say lambda is the wavelength, theta is the grazing angle. Okay, and this one was high energy E beam from a source like, let's say, an electron gun or something like that. Okay. And so there were, I guess, some what was that? Maybe after that the concept of Bravais lattice came. So Bravais lattice is Bravais lattice were few kind of structures. So there were the simple cubic crystalline structures. There were FCC, that is the face-centered cubic structures, and BCC, that is the body-centered cubic structures. Okay. Based on these, there were few topics we have learned. That is the packing density of this unit cells, and we have learned the number of atoms in a number of atoms in a unit cell, the concept of primitive cells, and we have learned also atomic structure, like the structure of silicon, the structure of diamond. Then we have learned about the Wigner said cell, and from that concept comes the concept of reciprocal lattices, and from that we have learned the Brillouin zones. So these were the basic recap of these week's like lectures. So we'll move on to the problem solving session where we'll take some problems and then we'll try to solve those. So the first problem for that case would be this. A new kind of a solid has a structure of a FCC lattice while having packing density of 1.54 grams per cc and the radius of atom is 0.197 nanometers. To find out the solid, please try it and try to get the answer. Then I'll share the how to solve this. Is anybody trying to solve this? So we'll wait for maybe 2-3 minutes. So what we have got in this is that value of radius is 0.197 nanometer, and we have got the information that the cell is a FCC structured cell, whereas the packing density, that is rho, is 1.54 gram per cc. You can't hear my voice?
Yes, a very good evening, sir. Now it's fine, sir. Now it's
Okay, fine. Try to
coming.
solve this. Yeah. If anybody gets the answer, please write it in the chat box or you can turn on your mic and say it. So for an FCC structure, I guess I'll solve this. So for a FCC lattice, the value of A is nothing but R multiplied by 2 root 2. From that we can write A equals to 2 root 2 into 0.197, but it's in nanometer. So it would be 5.574 into 10 to the minus 8 centimeters. From that we can get the value of rho, that is 4m by a cube into multiplied by the Avogadro's number, and from that we can write it as 4 sorry, yeah, so the m value would be rho a cube na divided by 4. From that we can write m equals to 1.54 gram per cc multiplied by 5.574 into 10 to the power minus 8 whole cube multiplied with 6.023 into 10 to the power 23 whole divided by 4. So the value would be m equals to, second, yeah, so it would be 1.54 multiplied by 5.574 whole cube multiplied by 6.023 into minus 1 divided by 4. The value of m would be 401.58 10 to the minus 1 or 40.158 grams per mole. My voice is coming or not? Maybe I'll use my headphones. Just a second. Yeah, so the value of this would be um, m equals to 40.158 grams per mole. Now we have to find a solid which has a mass near the same. So we know that calcium has a m of 40.08. So based on the basic assumption, we can say the solid is calcium. Now, if we change the question a bit, so let's say that if Avogadro's number was 8.3848 multiplied with 10 to the power 23, then what would be the atomic number? So this directly from this. Try to solve this. It would be easy, I guess. So if Avogadro's number is 8.3848 into 10 to the power 23, which is actually 6.023, so we are changing it with, I'll for the time being I'll write this here. So if we are changing the Avogadro's numbers to this, so what would be the value of atomic number? Try to solve this. Let's take 2-3 minutes and then try to solve this. So just change the number from 6.023 to this and tell me the answer. Just change the number. And for the mass, like try to use Google, find the nearby numbers.
Sir, 55.9.
55.9. Yeah, so use Google to find the solid with the nearby mass and then get its atomic number. There is a solid with 56. Find its atomic number then. So with the approximation, M comes out to be 55.98 grams per mole. Find the nearby solid. Or you can write it as 56, right? That is for iron, and for iron, atomic number is 26. So the answer would be 26. Now we move to the question number 3. Okay. So for question number 3, we have a value of Ek equals to cos square K. Okay. Now find out the expression of effective mass. We have already solved this. So we have got the effective mass. So try to solve this. Maybe I'll give a hint. So the value of effective mass, that is m star, is h cut square by d2e dk square. From this, try to solve this. Has anybody derived the answer? So I'll do it then. So we know the value of ek is cos square k. From that we can derive the value of d by dk, that is minus 2 sine 2k, and from that we can write d2e by dk square as minus 4 cos of 2k. So we'll have m star equals to h cut square by minus 4 cos of 2k. This is the value of effective mass. So we'll move on to the next question. So the next question is that a crystal have a lattice constant of 0.5. We have to find out Bragg's angle for diffraction with a wavelength of 0.15 nanometers. So Bragg's formula was this. Try to solve this. Find the value of theta. That's it. But in terms of let's try it. Then I'll explain. Please try to solve this, because it's a very easy one. You just have to put the directly the numbers, nothing else. Sine theta is nothing but n lambda by 2d. So we know the value of n, we know the value of lambda, we know the value of d. That's it.
So whether it is 8.6 degree
8 point?
6.
Yeah, that's the answer. So if there is there is no mention of the value of n, so we'll consider it as the lowest one if there is nothing written. So we'll take n equals to 1. So for that case, sine theta would be lambda by 2d, and that would be theta equals to sine inverse of lambda by 2d, and that would be sine inverse of 0.15 divided by 2 multiplied by 0.5. That would be sine inverse of 0.15, and that would be the value of 1506 radian, and in degrees it would be in degrees it would be 8.6269 degrees. So this is the value of that. Then we'll move on to the next one. That is maybe the fifth one, right? Yes. So in chronic penny model, in chronic penny model, we need to find out an envelope that fits the EK plot. There are several options. The first one is E equals to A by K. The next one is E square plus K square equals to A square. Third one is E square minus K square equals to A square. And fourth one is none. So which one is correct? And tell me the reason as well.
So the option for none of the
The options are,
so option for none of the above.
yeah, so that's the correct one, right? But why?
So because the value of E will be 8k square.
Yeah, but why not the first one? I got your point, but why not the first one? What happens if we increase the value of k? The value of e should be what? The value of
So
e should,
since the envelope forms as a parabola,
yeah. So because
so that's
for the increase in k, the e should increase, but in this case, what happens? The e is decreasing. So this is a wrong answer. For the next one, this is nothing but a circle. So a circle can't define the envelope, so that's wrong. For this case, it's a hyperbola. The same thing is here. So this should be like this. So you are correct. So we move on to the next one, question 6. That is, in chronic penny model, we have a periodic potential barrier of 1 nanometer with a height of 5 electron volts. Calculate the forbidden energy gap. Try to solve this. The barrier is 5, and the periodic barrier of 1 nanometer has a 5 electron volt height. So what would be the forbidden energy gap? Take some time and try to solve this. 1.01 EV. Not quite right. Try to recheck your calculation again. Let me recheck mine as well. But try to recheck your calculation. 10 EV. No. Try to recheck your answers. So, what is the formula you guys are using? Just tell me that. Any one of you just turn on your mic and tell me the formula. What's the formula you both are using? So, in that, the potential barrier is told as 5 eV, and the barrier is of 1 nanometer. So, the barrier height is 1 into 10 to the power 9 meters. Let me recheck mine one as well. Calculation. So this should be minus 32 minus 2 minus 32. Still waiting for that check. Just a second. Fine. So this term should be So anyone has solved this? So the formula would be h cut square pi square u naught by 2m b square. And so from this it would be 658 2 into 10 to the minus 16 whole square multiplied by pi squared multiplied by 5, and from this one it would be 9.1 into 10 to the minus 31 into 10 to the minus 9 whole square. Just delete this. Let's do this here. 6.582 into 6.582. This would be 43.32 into 10 to the minus 32 into pi into pi would be 9.87 into 5 divided by 9.1 into 2, that would be 18.2 minus 31. So just a second. So this one would be in EV, right? 5 into EV. So the value would be 3.32 multiplied by 9.87 by 18.2. So the values are 23.49. This one should be minus 1. So 10 to the minus 132. I guess I am missing some calculation as well. So if that's it, so this should be, this would have been like this. But just a second. Okay, so there's a mistake actually. We don't need to convert it back because otherwise we would have to convert that EV to joules as well. So if we put this in nanometers, so this would be like this, and this one would have been just multiplied by 1. So this would be the answer, 2.3449 EV. So with the approximations, I guess if we don't use the approximation, the answer would be, just a second, 6.582, 6.582 into 9.87 and multiply 5 divided by 2 divided by 9.1. So if we don't use the approximation, the answer would be nearly like this, or it may change a bit. So we'll move on to the next question. So this one, question number 6, right? We'll move on to the next one, which would be this. So we have a value of E of K, which is H cut VF mod of K of X, and this would be X as well. So VF here is the velocity, and we need to find out M star, or the effective mass. Try to get this. So to make it simpler, we know M star is H cut square by D2E by dk square. What is the value of this? So let's, like, sorry, let's just derive the derivative of this. So what would be the value? It would be nothing but H cut VF, and this would be plus minus 1, right? So we can say that this term is independent of K already. So what would happen if we just derive this? This would be nothing but 0. So M star would be undefined. Is it okay? We will move to the next problem. I guess we can end this session today here, and from the next session, try to be more interactive, and so we can discuss more hard problems and those things. So if you have any questions, please let me know, and then I'll try to answer that.
So for the sixth sum, there is a doubt for me.
Yeah, 6. Yeah.
So when I divide the value, I'm getting 117.3.
Yeah, so maybe I have there was a calculation mistake. So I have divided it on my phone because I'm not able to find my calculator. So you have just put this same values there.
Yes, sir.
Yeah, so let me recheck again then.
Okay.
There may be some calculation mistakes. Just I'll just recheck just a second. So you are getting 117.46.
Yes, sir.
Yeah. Yeah, so there were some calculation mistakes. Just a second. 53.3247 into 5 to 18 point. Okay, so by this approximation we get this, right?
Yes, sir.
So this would be 10 to the minus 1. So the value would be 11.746. So you're getting this, right?
Yes, sir.
Yeah, so someone has got, I guess, 10 EV. So yours one was also correct. So what is your name? Like,
Sir Padma Jyoti.
Acha, okay. So you have got an EV, right? So you have written there. Okay, that's fine. Then there was someone, Sandelia. So like maybe there was a term mistake or something that there were -1. So maybe because of that. So this is the correct one. So I have mistakenly. Oh, so I haven't, I guess, divided with, sorry, multiplied with the 5 that the term was missing. That's why. Because mine was 2.3 something. No? So this would be the final answer. So if any of you have any questions, please go ahead.
Sir.
Yeah.
So in seventh question, why we are taking the k value as plus or minus 1?
Because it's nothing but because it's inside the what do I say, like inside the inside this, right? So the point is that even if we get -1, it would have been 1 anyways. So we are just dividing it, just that's the one. So the okay, so I shouldn't have writ okay, so this is your question, right? It should be like this. So like it can be plus or -1. Even with that, it is independent of k. So anyways, with if we are differentiating with based on right with respect to k, so it would be anyways 0. So the value would be undefined.
Okay, sir.
Yeah. So we would have to get another way to find m star. Otherwise, we can't define it through this way. That's it. If you have any other questions, you can go ahead. So if are there any questions? There are many people as well. So if there are no further questions, I'll end this session here. So we'll meet again on Sunday from 7 to 9 next week. Thank you everyone for attending the session.
Thank you, sir.
Thank you.